Good afternoon, everyone. Welcome to the webinar series, which is organized by our Center for Advanced Multimodal Mobility Solution and Education, aka CAMMSE. My name is Wei Fan. I'm a professor of both civil and environmental engineering department at the University of North Carolina at Charlotte. I'm also the CAMMSE director. As many of you know, CAMMSE is a 5-year multi-campus Tier 1 university transportation center funded by the U.S. Department of Transportation that began operations in November 2016 under the FAST Act. We are a consortium of 5 universities, including the University of Charlotte as the lead, the University of Texas at Austin, the University of Connecticut, Washington State University at Pullman, and Texas Southern University. Today, we're really delighted to have Dr. Christian Claudel as our speaker. Dr. Claudel currently serves as a transportation engineering assistant professor in the Department of Civil, Architecture, and Environmental Engineering at the University of Texas at Austin. So who compares, huh? He received a master and a Ph.D. degree, both in electrical engineering from the University of California at Berkeley in 2009 and 2010, respectively. So he specialized in cyber physical system monitoring and the use of wireless sensor networks for environmental applications. The topic that he's going to present today is on a social spatio-temporal graph, convolutional neural network for human trajectory prediction. Before he starts, a couple of logistic announcements. First, as you know, we are going to record the seminar. And also, we're going to ask, you can ask any questions throughout the presentation, but we're going to hold all the questions until the end of his presentation. At that time, we're going to have a Q&A session in which Dr. Claudel will be happy to answer any questions that you may have. With that, without any further ado, let's welcome Dr. Christian Claudel.
Thank you very much, Wei, for the introduction. And it's my great pleasure today to give the seminar for this CAMMSE seminar series. So today, what I'm going to discuss is exactly this topic that you just mentioned, which is a Social-STGCNN. So it's spatial-temporal graph convolutional neural network used for pedestrian trajectory predictions. So the idea of this work is summarized in these 2 images. You can see on these 2 images that we are monitoring some area with actually a UAV, but it could be with any overhead camera. And we see people in this image. So there are people walking on the sidewalk. There are people entering this building. And what we try to do is to use machine learning to try to predict what people will do in the future. So it's really the objective of this project. And that was led by my 2 PhD students, so Abdullah Mohammed and Kun Kian, and also a colleague, Mohamed El Hosseini at KAUST, who is also specialized in machine learning. And this is really something that we have developed through CAMMSE funding, as well as through NSF funding through the CPS division. So it's really something that we have done in the past 3 years, thanks to the support of CAMMSE. So the motivation of this project is to address some traffic safety needs. So we all know that in transportation, traffic safety is a major issue. There are lots of collisions happening every day between pedestrians, drivers, bicyclists, and any other transportation mode. So of course, as you are moving, you are risking collisions, obviously. And it's a major difficulty in transportation, particularly in multimodal transportation, which is the focus of CAMMSE. So that means that in multimodal transportation, The problem is compounded by the fact that we have different types of modes. So you can have pedestrians, you can have bicyclists, you can have motorcyclists, you can have drivers. You could also have other public transportation modes, or you could have even autonomous vehicles in the future. So all these things have to coexist. And we need to have some solutions for safety that are scalable. So we need to basically adapt these solutions to the maximum amount of users. Right now, the philosophy is to address safety, and it's really the technology is emerging here. But most of the real safety advances come from passive safety, so how to improve the safety of cars, for example, in collisions, or through some techniques, for example, through geometric design of roads or through optimization of schedules, essentially planning the system so that you have the minimum amount of times. But it's very difficult to have a solution right now that is real time. So once all these barriers that are based on design have failed, then you can have a risk of collision. And we don't have anything that limits this possibility of failing. So the motivation for this project was the use of reality, and that's also another project that we have with the CPS division of the NSF. So how to use augmented reality to provide guidance information in crowded environments to all road users. The idea would be that we have pedestrians, we have bicyclists, we have drivers. All of them could have this augmented reality goggles. So here I'm putting an early version of the Google Glass. The Google Glass is actually not that great for this application. It's actually very inaccurate. The sensors are too noisy. In addition to that, the computational power is severely limited, so you can actually display text or bars, but you cannot display much more. You cannot display, for example, 3D graphs or 3D information. So it's not really that useful. But with that Google Glasses, we have worked a few years ago. So you can see, you can recognize maybe those who have been at UT. This is the front of ECJ building, and this was one of my former students in electrical engineering that has been working on this project, how to essentially track the position of people. So you can see the tracking is not perfect because the sensors are not that good. So we try to box this person. We are not using a vision for this. We are only using a tracker in the person, and we are using the coordinate system from the head. So we try to, so we have to essentially detect how the person orients his head, what's his position, and what's the relative position of other users. So this is something that we had tried, that was back in 2015. The technology was not mature at all for this, but now the technology is improving slowly. So we get more and more accurate sensors for a lower and lower price. So we could imagine that in the future, we could have essentially people that are tracked by some systems, for example, by cameras or by devices that we all wear, RTK GPSs or similar, that track our positions very well. We can also use the latest technology in augmented reality that allows us to superimpose with high accuracy the information in our field of view. So this is also something that is emerging right now. So augmented reality, the state of the art. Again, sorry, I forgot to define what augmented reality is, but augmented reality is using essentially some special goggles that display some information that superimpose over what you're seeing. So these goggles, for example, Microsoft HoloLens, they work very well indoors. So indoors, they can really detect where the walls are around you, and they can map information based on the walls, for example. But they fail to work outdoors, because outdoors it's very difficult to have a reference of position. So it's very hard to design a frame of reference around you and to track that. That's really a problem of sensors. If we have better sensors in the next few years and cheaper sensors, we can possibly now have very good goggles that work outdoors, including when you're driving or when you're biking, and you can actually now start to display information. And the idea for us is to display 3D generated reference trajectories. So how to, for example, tell you where to go. If you are a bicyclist, we can tell you, for example, turn left right now because a car is about to pass you, and we can display that really very intuitively in your field of view, not even as a message, but more as an arrow that tells you don't turn left right now or do this later, and that would be extremely easy for people to follow. So this is a more recent augmented reality goggle, but there are lots that are on the market right now. So they are not only 3D augmented reality goggles that can be used. We can also use possibly in-car head-up displays. So right now, again, the in-car head-up displays is an emerging technology, and the technology is usually 2D, so it doesn't display anything more than text and symbols. But we could do that in the next few years. We could have things that progress and that can display this information again in 3D. So with all this technology, the prime formulation is the following. So given a certain intersection, given multiple road users, how can we create in advance collision-free trajectories? So trajectories that avoid collisions. Obviously, we don't want people to collide. And that also optimize delays, because remember, we are operating a transportation system, so we don't want to avoid collisions without any other objective. We also want to make sure that people are moving. And usually these are conflicting objectives. We all know that if we try to minimize delays, then we take more risk, and of course we have more collisions. So it's really competing objectives. But with this new technology, what we think is that we could potentially have solutions that are more efficient than what are available right now. So this problem of creating collision-free trajectories that optimize delay, that's a classical control problem. So in the field, when you have multiple agents that you control, you can, for example, if you have multiple robots that are in a room, you can tell them, okay, go to that location, each robot goes to a certain target location, and you can create trajectories such that they don't collide. That's something that has been done before, obviously, and that is a topic of research. The main issue that we have in transportation is the uncontrolled agents. So when you have the ideal framework that everyone is a robot, that's great. Then you can tell every robot to move. But we are not robots. We are moving, and we have our own free will. So we take our own decisions. And how do we now handle this uncertainty in the system? Because that's where most of the uncertainty comes from. If we have lots of robots, we can coordinate them. And there is not much uncertainty unless a robot is failing. For example, there is no special uncertainty to take care of. But if now you have a lot of people that can do anything, how do you create that? And the main issue of these uncontrolled agents is that essentially we cannot now anymore guarantee that we won't have collisions, because people can do anything at any time. And if you think about the usual traffic situations, when you're driving, for example, you can't guarantee that you will never have collisions with the vehicle in front of you or with the bike that you're passing, because they could potentially collide with you. So we still try to optimize, and we are very good at it, because in the end, human drivers have a very small amount of accidents. It's much harder to do with robots, though. So this is the paradigm that we are thinking of. So the future, we could have intersection managers that control intersections. These intersection managers would receive data from human-driven vehicles and also pedestrians and any other mode of transportation. They receive data also from possibly autonomous vehicles, and autonomous vehicles, it's much easier for a autonomous vehicle, to give you the trajectory forecast, because that's a robot, so it can tell you what it intends to do. But for the others, that's much more difficult. So here, our objective is to predict what these people will do, the human-driven vehicles or the pedestrians. So in this work, it's many pedestrians. Send this information to the intersection manager. The intersection manager would compute these trajectories that are safe, and then it would send back this information to again everyone, so to the control people, so to control the drivers and the pedestrians, as well as the autonomous vehicles, because it could refine the information and give now a new target trajectory for the autonomous vehicle. But all this depends a lot on the humans. So now we have a human performance model. What are the humans going to decide in the future? And it's a feedback loop that happens, because you have guidance commands that are sent to the humans. You have the response of the human as well, because when you control humans, they won't respond exactly to your inputs. So we have to take that into account as well. And the information that we gain from the human performance model that is used to predict the trajectories, that's also something that we feed back in the intersection manager as well, because in the end, when we create the trajectories, for people, for example, that are not trajectories very well, we need to essentially, or people that have lots of uncertainties associated to their motion, we need to take that into account when we predict the trajectories. Okay, so here we're interested only in the subset of predicting the path of uncontrolled agents. But of course, the complete system requires a lot of other advances in a lot of other fields. So predicting the path of uncontrolled users, how do we do this? So we do this by using cameras. So we don't have tracking devices that people would carry, because it would be very impractical to ask people to carry devices, and what if the device is not working? So instead, what we are thinking of is to use camera-based systems. There are lots of cameras available everywhere now in cities, and with cameras, whether it's drone cameras that are installed on buildings, we can actually usually detect users pretty well. So that's done already, and a lot of people are using these techniques. For example, here we can detect pedestrians. We can detect also cars, bicycles, etc. So for bicycles, it's a bit harder because we don't have the same performance in tracking, but that's generally good. So we can predict positions and speed. We can get position and speeds from these cameras, but the problem is that we cannot use these cameras to predict directly what people will do in the future. So you can see here the tracks, these lines correspond to what pedestrians are doing in the future. So again, as I mentioned, this is critical for path planning, because the trajectories of some vehicles can be easily predicted, but the trajectories of some other vehicles cannot be predicted easily. So easily predicted trajectories would be, for example, autonomous vehicles, ground transportation system, for which we know predictably what the path will be. But for the rest of the system, we don't know what people will do in the future. So we want to use the camera cues, essentially information, to predict these paths. Right, so now that I've motivated the pram, let me just present you very briefly the outline of this talk today. So I'm going to talk about this novel architecture for predicting the user's path, and this Social-STGCNN, so spatial-temporal graph-based convolutional neural network. And then we're going to discuss the main features of this algorithm. So I'm not going to go too much into details, but just a flavor of how the algorithm works and what are the main features. I'm going to then compare this algorithm with state-of-the-art algorithms. So for this comparison, we have used extensively a very large data sets available in the literature. So the good thing in the machine learning community is that people tend to use the same training and validation data sets, so that you can really compare the performance of algorithms on some benchmark data sets that are set. So here, that's what we're doing. We first evaluate the performance in tracking error. So that means how accurate are we in tracking the position of in predicting the positions of pedestrians. And then we also evaluate the performance in terms of computation. That's also a bottleneck, because if the algorithm takes 2 seconds, for example, to predict the path of the user in 2 seconds, the information comes too late. So we need really something that is very fast. A word just about the predictions. We are using very, very short horizon predictions. We don't try to predict what the users will do in the next 10 seconds or in the next 20 seconds, but we really try to predict what they are going to do in the next 3-4 seconds. Any information that you have ahead is important, because even if you predict only over 2 or 3 seconds horizon, that still gives you a lot of head up to adapt your trajectory or to modify things. We try to get essentially the same performance as us. And when we are driving also, when we see, for example, someone about to cross the road, we also have the same short horizon predictions. We don't try to predict what people will do 30 seconds in the future, but what are they going to do in the next 2-3 seconds when we are going to be next to them when we drive. And finally, I will present some other research activities of the lab that are also related to the topic as well, more in robotics, and finally the conclusion. All right, so here, let me just show you briefly the background of this algorithm. So a lot of work of pedestrian path prediction, because it has many applications beyond safety. For example, people might use it for advertisement and for other applications to determine how people react, for example, to ads, or what are they up to. This is something that has gathered quite a bit of interest in the past 5 years. Say. So It's a complex task because pedestrians evolve, so they all have their own free will. They can do their own tasks. And also, there is not a complete independence between each pedestrian. So, for example, when pedestrians move, if you meet, for example, a friend, you're going to either walk with them or you're going to talk with them and then move away. You're going to also avoid pedestrians that are in a direct collision course with you. So there is really some interaction that is modeled. And with previous work, so we simplified a gap with earlier work on the same topic. In that earlier work, modeled social interactions using pooling techniques. So when you're doing learning techniques, you are getting some camera data. So you're getting a lot of information from this camera. You're extracting features, which is a subset of this information. And because that's still too much information, you have to use pooling techniques. So pooling techniques are essentially a way to downsample the information. So how to reduce information instead of taking the entire set of information, you just pick some elements, and then you try to predict from there. So of course, when you're removing some information, you're losing information, obviously. So we wanted to use a different approach in this technique, to use non-pooling techniques to achieve still some good computational efficiency. And a second gap of existing methods is that they are iterative. So they use recurrent architectures in which we take the current position, we predict the next position, for example, the position in the next half a second, and then we use all these next position to predict the subsequent position. So for example, you have the current position, you use the algorithm to predict the position in 0.5 seconds, then you use that 0.5 second position to predict the position in 1 second, and so on and so forth, until you achieve your time horizon of, say, 3 seconds. And when you have a recurrent architecture like this, you're going to accumulate errors because the first position will not be perfect, the second one will be even worse, the third one will be worse, and so on and so forth. So you will have very quickly some error that will grow up very fast. And of course, the more error you have on the prediction, the worse it is, because what we want is to have something that is reasonably accurate, that still doesn't overpredict. Because if you say that people can be everywhere, it doesn't help. We already knew that. So we want something that is still giving you a reasonably good distribution of what people will do in the future. And of course, exceptionally, sometimes you can also go off, but we want to be reasonably good. So this is how the algorithm works. So we have the pedestrians or the bicyclists that are detected. We have a bunch of people here that are around, and then what we do is we build a graph of these people. Build there some edges and some vertices to denote the level of interaction between all these users. Then we use that algorithm that I mentioned, and this Social-STGCNN, over a single pass. And so that means that we don't have any recurrence. We don't reuse the past information of the intermediate predictions. We predict everything at once. And finally, we use the predicted future trajectories to know what will happen in the next steps. Just to give an idea on the way it works, we don't use only the current frame of data. So we don't use, so if we have some camera data, for example, if I look at this data set, so we have some camera data, we know where people are right now, but we don't use only that information. We also use the past information. So we know what they did just up to now, and we use that information to predict what they will do next. So we use the past information up to now. Of course, we don't use any future information. Obviously, that would be cheating, but we use the past information, and then we predict what will be next. We don't use much past information. We don't use what these people did half an hour ago. Of course, we use only the past, I believe, 2 or 3 seconds of data, only to predict what they will do next. So this is again what I just mentioned, and the interactions of users are modeled using this graph, so that's the key novelty. And then the predictions are done over a certain time horizon, but not frame by frame or not with intermediate time steps. All right, so now let's discuss a little bit about the graph model. So if we have a certain set of users. For example, here on this image, you can see you have the red user, the yellow user, and the green user. So you just have a single user. The fact that you have 3 people each time, it's because you have 3 frames, so three images that you have to analyze. So what we are going to do is we are going to look at the respective positions of these users, so the red, the green, and the yellow users. We're going to build the graph, so you can see the graph connecting the users at the first time step, then the graph connecting by the users at the second time step, and the graph connecting the users at the third time step. And what we built was an empirical adjacency matrix kernel function that would model the interactions between pedestrians. So that's where a little bit all the physical intuition goes. So we have a certain set of parameters that are in these graphs, edges and vertices. So we have a bunch of information that flows there. And what we are doing is we are using some function to approximate the interactions that they will have. So here we use some information that is based on the coefficients that represent the positions here, but not just the current position. Of course, it represents the sequences of positions as well. And we have a model that use an inverse function here in such a way that we essentially try to make sure that people repel each other in a sense. So if you're on a collision course, obviously you will try to move away from collision, and you will not collide head-on. Usually that's the classical situation. We have the thing is that it's a little bit more complicated than a direct function, because we have still a temporal component that is taken into account. So if we fix time, of course, we have just a certain function that here tries to penalize when we are on the collision course. But in reality, it's a little bit more complex, because, for example, if people are walking together on the street, you don't want to penalize this. This is actually some normal thing. And the system learns how to make the difference between this collision course and regular interactions that are more likely. For example, when someone walks next to someone else, or when people meet and talk and walk together after that. So all this information is what we try to learn essentially. And I believe also for this approach, machine learning is the right way to go, because we don't have any other model of interactions. It's very difficult. We look at the literature, but it's very difficult to look at reliable models of human interactions. Humans have a lot of diversity in behaviors, so it's very difficult to learn essentially what people will do. It's much easier to use the information, the past information of some humans. So because we track people for some time, so we know what they're up to and that helps us predicting what they will do next, essentially. And for this model also, we use future positions. So we model them not just at a single point, but we really try to model the distribution of the future positions. So that's very important, because if you want to create collision-free trajectories, you don't want to have just a single possible what people will do next, because we know that this has some uncertainty. So what you want is to understand what is the uncertainty range of what people will do next, so that your future paths avoid, so you avoid collisions essentially robustly in a sense, so that that you know that despite the uncertainty, the trajectories that you impose to users will be always safe, no matter how much. I mean, based on the uncertainty that you're seeing and that you're estimating. So the model inputs and outputs we use for this model. So we use the inputs, that is video data. Here, that's what happens on the left. You can see some frames that are extracted. I believe it's from the ETH dataset. We have a sequence of video data that is obtained. So we then use some classical machine learning algorithms to detect where people are. So that's really something not novel at all. People have been doing that all the time. And once we have that, we have now a graph of where people are. So then we create this graph convolutional neural network layer. So this is the novelty of the algorithm. And so we embed everything into a graph. We then use the time extrapolator. That was the name coined by my student Abdullah Mohammed. And so here the time extrapolator is essentially a way of saying that we are not predicting over a single horizon, but we predict over a series of horizons at the same time. Once this is done, what we get as an output is the predicted distributions. So we start with an input that is just positions. And at the end, what we get is starting from each of the position of each user, what is their predicted paths in the future? What are they up to according to the algorithm? Again, the algorithm is not perfect, but that's what we try to achieve. So this is an example of trajectory computation here. So I just put some sequences of images that we have obtained, again, I believe, from the hotel dataset here. So this is some overhead image of, again, some area. I believe this is a building here, and this is a sidewalk. We have people walking here, and see here there is one person that is walking. You can see the trajectory here as they move. So they create a certain, sorry, there are two people that are moving. So they create some trajectory as they move. So you can see these dashed yellow lines as they move along. And then after some time, we try to predict. So we use essentially all this past information of what they were up to that point, to predict now what will be their paths for the future, again, according to the algorithm. So here you can see that we predict that people will keep working together, and that's something that is reasonably realistic. Now, just in terms of quality, just a word about that. It's something that has been also very interesting to see that people in the machine learning community, they have been working at trying to make this algorithm work in the best way they could, without comparing necessarily very simple naive methods. And a naive method here to what people do next is to use their current position and speed and just keep the frame going forward, saying that, okay, let's assume that people keep their speed all the time. Where will they be next? And you can do that, and you can with that you can predict what people will do next. The only problem with this approach is that actually this approach is not too bad, and the results are less accurate, of course, than this algorithm, but they are not totally inaccurate, and they are quite accurate. And in fact, they are more accurate than some other reported algorithms. So it's really something that you could try. But one of the problems associated with this is the fact that we don't capture the uncertainty. So if you use the current position and the current speed to predict what people will do next, you still have no idea about the uncertainty of your prediction. So this is really something important. Here, at least, we know that the paths look realistic, and the uncertainty looks realistic as well. We don't expect them to deviate by much more than this. And that's also something that was noticed by my two PhD students, Abdullah Mohammed and Kun Kian, when they looked at this problem from a human standpoint. They also thought about trying to infer better than the algorithm. And in fact, it's actually quite difficult, because they told me that many times it was very hard from looking at the video data only to try to know what people would do next. So there is obviously a limit. We cannot do much better than humans. Obviously, I think we are the best at predicting this. So we have to also stay realistic and realize that machines will not ever be perfect at predicting this. We can at most achieve, I would say, human level accuracy as we progress on this topic. Okay, so now let's compare this algorithm with state-of-the-art algorithm. So now that I just briefly gave an overview of this Social-STGCNN, we want to compare this algorithm. So what we did is we took 5 large data sets, so that correspond to I believe hundreds of gigabytes of data or terabytes of data. So that was really a lot of data to process. We extracted all these human trajectories from these data sets using a classical machine vision algorithms. And then based on these positions that we have obtained, we measure the performance of the algorithm with 2 metrics. So the first metric is the average displacement error, which means that along the trajectory, Here we are summing over the trajectory. So along the trajectory, what was the error, the average error that we are getting in the least squares? I mean, in the norm 2 sense, between the positions that we are predicting and the actual position of the user. So that's the average error. And finally, the final displacement error sum over all the agents. Here we sum the errors that are at the final time only. So we don't look at the intermediate errors, but we just look at the final error at the end of the time horizon. We also analyze other things. So things that are important in machine learning are also parameter efficiency. So how many parameters do you need to do the prediction? The lower amount of parameter, the better, because that means it will be more robust and it will also take less time to compute. We also analyze the data efficiency of the algorithm. So that's also something important. You may have some machine learning algorithm that is very efficient at predicting, that is very accurate, very fast, but it could be that you need actually a ton of data to train the algorithm to understand how to predict. So here this data efficiency is also what we try to evaluate, meaning if we take a subset of data, if we take a small data sample, can we still have a reasonably good prediction? Can the algorithm predict quickly how people will do? So can it learn quickly, essentially? This is the main result of that we showed in this paper. So all this was published at CVPR this year, a few months ago. So I believe last month actually. So in this table, I show the performance comparison over these 5 datasets, so ETH, Hotel, Univ, Zara1, Zara2, and the average performance on the last column between all the algorithms that were reported in the state of the art. So you have this linear algorithm. So this linear algorithm is really the simplest algorithm that I just discussed. And it amounts to taking the current trajectory of people, the current speed, and then predicting what people will do next. So it's really something that very, very basic and simple. But you can see that the performance is already not too bad. I mean, it's of course it's twice worse than what we have right now, but it's not completely bad. I mean, it's still reasonably accurate. Then you can see all these algorithms here that were reported in the literature, and the algorithm that we propose here is having a better performance in average across all these data sets. So you can see that sometimes it's not performing perfectly, but in average, definitely the performance is better than anything reported. So that was some interesting result and a significant result. In average, we get a 20% lower error in average displacement error and a 2% error in the final displacement error. So these are significant. Even though it's not a lot, it's still significant statistically, given the metric that we use and given the amount of data over which we have tested. So it's the problem of machine learning also is that it's diminishing returns. So as we have more and more algorithms that are proposed, it's harder and harder to improve over the proposed algorithms to get something better. To analyze the parameter efficiency and the computational complexity. So parameter efficiency means that we want to have a lower number of parameters. And here, that's really where the proposed algorithm is really making a difference. So we are a little bit better in terms of error, but the main advantage is that we really need much parameters than what what other reported algorithms need. And you can see here that if we compare with the previous algorithm. So I believe there was a question here that was asked. Sorry, let me just go back here. I'm not sure how to access because I saw some very quick text that disappeared, and I need to just okay. So I think I will answer probably the question later if at the end probably that might be easier. Right. So let me just go back to my presentation. All right. So here, in terms of parameter efficiency, we have really a higher performance than currently reported algorithms. So in particular, you can see 35 35 times less parameter count than this algorithm here. In average, really almost 10 times less parameters. So it's really an order of magnitude better than other algorithms that are currently reported. And we have also a much faster inference time. So we need only 2 milliseconds over a classical computer to predict, while other algorithms need up to 1 second to compute. And really, when you take 1 second to compute something, that's not a very good performance, because you are already halfway through the prediction horizon when you give the result. We also believe that the fast prediction is very important, because we vary parameters and we sample essentially trajectories. We can actually do something that is more robust if we use a Monte Carlo approach, for example, to samples. Right, so let me just go next to data efficiency. So I just don't get any feedback, so I'm not sure. Am I still connected? Okay, I see. It seems that everything is connected, but we get the confirmation. Okay, everything is fine. Okay, I can hear something. So good. All right. Sometimes I have internet. I just want to make sure that I'm just in track here. Okay, so then data efficiency. So data efficiency, again, is related to the ability for the algorithm to predict with little data. So what we want is the algorithm to learn quickly how to predict these trajectories with a small amount of data. And here, that's also something that is very interesting for the algorithm that we have introduced. We need only, in average, 20% of the data used by state-of-the-art algorithm to exceed their performance. So, for example, here, we compared this with generative adversarial neural networks. So it's a particular type of neural networks that is learning faster usually. So it's really a great advantage of GANs. You start really with a fast convergence very quickly. But you can see that with only percent of the data, we already exceed that performance. So that's really something that was very interesting. That was very interesting for us. And we saw that even for very, very small amount of training data, we already exceeded the performance of the generative adversarial neural network. So it's really some commendable results. So that's for the description of the algorithm. Now let's discuss a little bit more about qualitative analysis. What does the algorithm predict in the end? So it's hard to describe everything here. I just made 2 slides to show some example results, but of course it's hard to summarize in 2 slides what happens in tens of hours or hundreds of hours of video data. Obviously, I don't show here necessarily the bad results, and there are some bad results in machine learning. Because it's a black box, it might work very well 99% of the time, but there might be some errors the rest of the time. And we all know that autonomous vehicles, for example, are not perfect because they might work very well in demos, but it may be that if you have the right sequence of events, the machine learning is giving you a very, very bad advice or a very bad prediction. So here, we compared qualitatively the performance of algorithms. So here these two algorithms. So here we just varied the kernel function between these 2 approaches, and we compared that with SGAN. So again, a generative adversarial neural network that was proposed in the literature for the same application. And you can see that here with these trajectories, our trajectories are more realistic somehow for these examples. So again, these examples are typical, I would say. That's what happens most of the time. Of course, you can find carefully, if you look at the dataset, an example where SGAN is doing better on one example or on a few examples than the proposed algorithm. But in average, these results hold, and the performance is more what we expect. So you can see here that, for example, this trajectory, this path here that we predict is more realistic than the GANs who would think that people will turn. So this is probably because people had some slight motion that were suggestive that they would turn in one direction, but in the end did not. Here, that's also some other examples where we have we have predictions that are also more realistic and that really encompass the future trajectories with respect to GANs. But again, that depends on the kernel function. You can see that here, if we take another kernel function, we have results that are worse. So here, of course, we optimized with that particular kernel function. We have also some interesting results in the sense we tend to avoid head-on collisions with pedestrians. And for example, you see that here the prediction was that 3 people, I mean, they are really on the collision course, but in fact, they are really avoiding the collision. And that's the behavior that we try to encompass. Here, if you use that generative adversarial neural network, or if you use a classical simple linear prediction, you would be on the collision course. And we all know that when you look at people from a distance, that's not what they would do. Of course, they could do that. And you could also have 2 pedestrians colliding if they don't watch and if they are watching their phones, for example, but that's not the typical result. So that's why we have a good performance again in that. And we can also model more complicated interactions with multiple users, where we see also that people tend to move away and people here tend to work together, but again, not colliding like what is predicted by the SGAN algorithm, more something where all 3 people here are working together and steering clear from that person working in the opposite direction. These are some examples also of results again on datasets. So we can see that, for example, some behaviors that are learned. So we really try to learn the different social behaviors, collision avoidance, parallel walking as well. That's something very important. So, for example, when people meet, so we have some examples here of behavior where people are working together or where they are meeting. The merging of people as well to have something that is realistic. So you can see that sometimes you get some bad results. For example, the merging here is reasonable, but the merging here where people are really colliding is bad. So that again can happen. And here, similarly, you can get some divergence of these 2 people working together, move away from each other, and that's not something that we would expect again because they were working together. So that's again, there are some errors. So here are typical errors that you can get. So some failures in prediction, for example, people moving apart from each other, like in this case, or coming back. These are again some misses of machine learning, and it's very hard to know the cause of that because it's a black box essentially. So you can't always have good results. These are picked examples that are really picked out of the dataset that we add just to also show that the system is perfect. But we hope that in the future we'll have something more efficient, more accurate, and that will have less errors in finally, I want to show also some other research activities. So I presented in this presentation the Social-STGCNN, but we are also doing a lot of other activities in the lab. I want to give a quick summary of our other contributions in transportation. So we have been working on traffic flow monitoring with these inertial measurement units. So that's something that we have done in the past 3 years, and now the project is complete, including some tests in Austin. We have also worked on traffic flow modeling and control. So this is some example work that I've done with my former Ph.D. student, Michele Simoni, on optimization of flow. So we have worked on fast semi-ethical solutions for transportation. We have worked also on integrating arbitrary microscopic flows to simulate delivery vehicles and for example, urban vehicles, ground transportation vehicles, fast solution algorithms as well. Of applications of this work that I just mentioned. So this is a state estimation, how to estimate the state of traffic on the highway. It's again a density map, and this is a space and this is time. So how to predict based on measurement data, how to control traffic. So we have worked on optimization of delivery vehicles, of buses. So here this is modeling bus bunching and trying to minimize bus bunching using again PDE flow models, and how to control them in real time so that they don't bunch. We have worked also on other control parameter, more control of flows, so how to do boundary control or control of speed limits to optimize traffic flows. Now, more closely related to what I'm showing here, we have also worked on the control of unmanned aerial vehicles for some applications, and this application is flood monitoring. There are lots of people that have worked on UAV control for traffic monitoring. In fact, we have worked also on this as well with Professor Boyce at UNC. Here, this project is more about how to use a set of UAVs and how to control them for floods. So it's somehow related to this problem that we had here. However, it's a control problem. It's not an estimation problem. We try to control now agents, and we don't try to estimate what they'll do next. And the big difference also is that here we are using a partial differential equation to model the flows here. So this is the watershed of Austin. And we try to use here the partial differential equation, the shallow water equations that describe how the flow will propagate in the river here, and we try to essentially use that information together with the topography map to determine how you should steer the UAVs. So if you have a set of UAVs that sense floods, how should you steer them to maximize the information that you gain over some time horizon? So imagine that you have a flood that's coming. You don't know if there is a flood at all, but you have just 5 UAVs. How should you assign their path in order to maximize the information that you will get, for example, over 10 minutes, and to get the most complete, most accurate map of the current situation, right? Some other research works. So here, the Guadeloupe team of UT. So that's something that is in parentheses, obviously, because of the COVID, but we had worked a few years on how to make Hyperloop systems. We have participated to 3 competitions actually of SpaceX in the past 3 years. And actually this year's competition was cancelled by SpaceX way before the COVID situation. So I don't know if they predicted that in advance, but this is really surprising. So we couldn't participate to this competition. This year there won't be any competition, but we hope that there will be competition years, and we are still working on how to make a pod that is using air bearings. So it's one of the few pods that are available that use this compressed air to try to float and to be essentially a system for transportation. All right, so now let me just quickly conclude this work. So what we presented here was the Social-STGCNN, so an algorithm that can be used to predict trajectories in the future, to predict pedestrian trajectories, of course, in this work. But what we would like to do is to extend it to any other application. So predict what drivers will do, what bicyclists will do, what other modes of transportation will do. Of course, in the case, for example, of drivers, you would have more information potentially that would come from the car itself. So for the pedestrians, we only can get information from cameras that are filming overhead. But for other vehicles, you could think that we could also share information, because all these new vehicles are filled with sensors. We have information from all the sensors. You could have also information from the driver itself, because we can, with new cameras now, with inside cameras in a car, you can know what people are looking at. You can know their head motion and so on and so forth. So with all this information, you potentially have even more accurate predictions of what drivers will do than what we can get with pedestrians. So any advance there is to take, because each time you get more information, you get a system that is more efficient and safer. So what we want to do is to implement this algorithm in the future to try new paradigms. And we also want to extend this algorithm to partially controlled situations. So in this situation that we had here, we don't know what the pedestrians will do next. We don't know what they are supposed to do in the future. However, there are some situations, and if I go back to the presentation, to the original slide here, remember what we want ultimately is to have a system that is controlled. We want to have an intersection manager that issues guidance commands. And the guide go back to everyone. They will go to autonomous vehicles, to driven vehicles, and to pedestrians. So here, if you have a pedestrian that has some guidance information, how can you now know what they will do next? So you know what they are supposed to do next. You tell them, go there. But what are they going to do next? Between what you should do and what you will do, that's not the same story. And you have some slight deviations. Obviously, you have people that don't track their trajectory very well. You have people that will do something else, that will forget about it. You have the same issue for drivers. For example, if you tell drivers what to do, there are some people that are distracted, that are not paying too much attention, or there are some people that are just not very good at driving, that will not be very accurate. So all this information is something that we would like to predict as well, because that's the second part of the system, predicting what people will do when they are supposed to be controlled. And if you together, now you can have even more realistic and more accurate trajectories and potentially increase the performance of the system. That concludes my presentation for today, and I'm ready to answer any question.
Okay, thank you, Dr. Claudel. It's great presentation, huh? I think we have one question here. I think the question is, how did the model include the interactions between pedestrians? Is that possible to revise the predicted trajectory of pedestrians in order to account for the collision avoidance behavior among pedestrians when there is a conflict between them?
Yes, so we take that information into account, as I showed on this example here, for the qualitative analysis. We try essentially to learn these social behaviors, the collision avoidance and parallel walking and other behaviors as well. So right now, these behaviors are taken into account through this kernel function for the adjacency matrix. So we have this, if I go back in my slides here, we have these functions that take into account these interactions. And because we have a sequence of past data that we use to predict the future, we essentially determine if, for example, people are working together, it's fine, they are working together. If people are on a collision course or they are working on the side, we also have the corresponding information because we have a time varying function here. That's through this information that we try to predict what people will do next. It would be also possibly other information that we could take into account, and that's also something that we could do in future work, which would be to take into account also simply the scene that we have as well, because there are some cues, some body cues, etc., that people have that also give a lot of what they are going to do next. So that's something that is very complicated to do with state-of-the-art algorithm, because it's very difficult with currently available algorithms to, for example, detect the gestures and classify the gestures or the head motions and so on and so forth. That's something that you can do as a human very easily, but machines still struggle to do this correctly. But I think that would be a very interesting development if we can achieve this.
I see. Thank you. And let's see. So this is the only question raised here in the box. So yeah, so I think Dr. Qi has a question here, right?
Oh yeah, Dr. Fan, yes, I have a question. Chris, I think you did a very good presentation to present this research. It's a very interesting research, and I think it's also very challenging, right? As predict human beings' behavior is not easy. Yeah. So I have a small question about when you build your model, because you introduce your the background, the overall motivation for your research is to try to use your results of the collision in the future when we implement the autonomous vehicle, because autonomous vehicle will interact with the pedestrian. So my question, do you think about the impacts of vehicle on the pedestrian behavior when the vehicle, close to the pedestrian or approaching to the pedestrian, their behavior may be different. For example, they will be more closer to each other, try to yield to vehicle.
That's right. That's a very good question, and in fact, that's related also to this. I mean, that was our primary motivation to put this adjacency matrix kernel. Even though, unlike what you mentioned, we haven't tested that in a situation where we have a mix of pedestrians and vehicles. But we expect that with pedestrians and vehicles, through a proper adjustment of this function, we could take into account the interactions with vehicles, and for example, the fact that people are afraid of vehicles, and especially when vehicles are closing in fast. All this information, I believe, could be encoded by the same type of adjacency matrix function. The only problem is that we couldn't test it very well because for some reason, everyone that is doing the testing in the machine learning community using these datasets here, these 5 datasets, and these 5 datasets are purely pedestrians. So some of them, for example, I believe this one was at Stanford, if I remember correctly, and it was just an overhead camera that was monitoring simply a purely pedestrian crossing. It wasn't. It was within the campus of the university. So there was no car involved, just bikes and pedestrians. But I think definitely that would be some very important thing. That's where I believe learning can help to predict what people will do next much more accurately than simple naive models that would take into account just what the current speed and positions are. Because we all know that even if you haven't seen the car, as soon as you hear something, you see something in your vision, you're gonna move back, and that's something that can be probably learned as well.
Thank you. Very interesting.
Thanks.
Okay, thank you, Dr. Qi and Dr. Claudel. I think we have one more question, which is Brandon raised this one. So have you looked into multimodal output?
Multimodal output. So here, I'm not very sure that I fully understand in multimodal. Oh, you mean is it in the sense of multiple distributions in the outputs? So not to have a single mode, for example, for the Gaussian, or okay, yeah, perfect. Okay, if that's, yes, definitely that's something that we also tried to. We try to use a Gaussian mixture model where we have multiple modes, and definitely that's something critical. So you can see here that in the prediction, sometimes we predict some things that have also multiple modes. For example, here you have your path here can split into 2 directions. Even though I'm not very sure of the significance of this prediction, that's not something that we have yet fully on this algorithm because we use only a single Gaussian to capture the future. So here we describe the trajectories, some kind of Monte Carlo approach where we vary some parameters slightly and we try to predict what people will do next. But definitely that multi-modal thing is very important for the future. Particularly, for example, if you have someone next to, for example, a crossing, are they going to cross, or are they going to stay, or are they going to walk back again? There are lots of situations in which things branch. When you have a bike, you could go straight or you could turn left, and predicting these modes here is something that will be critical for the future. So it's really we use already the features in the image. We already use the features of the ground. So we use the ground image that we extract, and those features are important because, for example, if you have a road and if you have a sidewalk, we learn that the sidewalk is for walking, and you can go in or out of the building. So all this is learned, and that's an important assumption. We haven't tested the situation in which we have a real intersection with ground markings, but we believe that the algorithm should also learn the signification, the meaning of the ground markings, and that would also help us to now determine this splitting. So we can already encode this split multiple modes through the variation of the parameters and the iteration, but I think it would be better to handle it as a Gaussian mixture model, where we have, for example, 2 probable paths or 3 probable, 3 most likely paths, and what are these paths going to be? Thanks for the question.
Okay, thank you. Thank you, Brendan. Thank you, Chris. So we do not have any additional question here listed here. So anybody, any participant here, huh? Do you have any further questions? You can ask question directly, make it more interactive. Yeah.
Sure. Okay. I think I saw just a question of Shauzi. So the ground truth here that we are using is this complete video dataset. So we use the dataset, we extract the position of every user in the video data. And the ground truth for us is to look at what people will do next in the future. So we the current paths, and in the future people will do some other trajectories, and we still have access to the future because we have the complete video. So we do at every time step, at every image of the video prediction, but we have the ground truth. We know what people are really doing from the video because we still have access to the complete video up to the end. That's how we compare the performance of the algorithm. So we try to, it's like watching a video and stopping at time 0 and then trying to see what will happen next. Guess what will happen next. Max.
That's a great question. And so no question here. So any more questions?
Chris, this is Randy.
Yep.
I'm curious if you guys have looked at application of this concept to bicycles.
We have tried to. Thanks for the question, Randy. And actually, that's something that a primary motivation. And in fact, initially, I started to work more on the vulnerable user side because of the advantage of these goggles. I mean, these goggles, technically, anyone can wear them, even bicyclists and everyone, just like sunglasses. So it's really something very portable to carry. And also, I know that basically safety is really a concern. A lot of people don't want to use bikes for this reason. Now, the problem that we have for bicyclists is first the lack of data sets to test the algorithm. So it would be, if we had good bicyclists that I think large scale, that would be very interesting for us. I think there might be some data sets, but not that we are aware of, because in the machine learning community, people haven't. So there is this first difficulty. The second difficulty is that for bicyclists, it's actually difficult to predict the position and the state of the bicycle. I'm not sure if this has progressed, but I know that even last year or 2 years ago, it was, I believe it was like 60% efficiency at capturing position of bicyclists. I'm not sure if in the data that you are using on the bicyclist, you can have some boxing of the bicycle that is very realistic and extraction of the trajectory. But I think that was one of the difficulties we had. So even if we can box the bicyclist very precisely, it's also to know what is the state of the bicyclist. So what is, for example, what are they, how strongly they are pressing on the pedals, how they are moving the handlebar, all that. I'm not sure if we can get this very reliably with video data from the state of the algorithms to process video data. But that would be something very important for us. Basically, it's really something that.
Thank you, sir.
Yeah.
Thank you,
Thanks.
Dr. Macmil. So there's one more question here.
Sure. Yep. So I saw just a very fast question, but I couldn't read it. Sorry. Do you have it somewhere?
Yeah. Other than the neural network-based models, will there be any chance that the tree-based models can be developed to solve the problems? Yeah.
Yeah, that's a very good question. We haven't investigated tree-based models, but yes, there should be some potential there as well, and especially because you have also some divergence, some branching. Now we tried namely the convolutional neural networks because it was what most other people have been using, and that has also some advantages also for CNNs have the advantage that they have worked well for image recognition, so we wanted to start working on that to try to extract some robust features that could be used for to somehow boost the trees to make sure that you get some reasonable accuracy and reasonable robustness, I would say, so that your tree doesn't grow too much. We haven't investigated this yet, but definitely that's something that could be of interest. And I believe there was one more question. I'm not sure if.
Okay, thank you, Chris. There's one more question here, huh? The question is the ground truth trajectory also has the same length? Or if not, how do you process long trajectories?
Yes, so here the ground truth always have the same length. So we always use, I believe, the last 4 seconds of data to predict the next 3 seconds of data. So no matter which dataset, it's always the same length. And we use the same parameters as the other teams that because all of them are using the same benchmark video data, and they use the exact same parameters. That's how they compare all the algorithms. So we use the same as the others. We use the same parameters, and because so all the trajectories will have. Trajectories will have, of course, different durations and all, but we predict that every single step of the image, we redo the prediction over and over, and we look at the average performance error of this process.
Okay, thank you, Chris.
Okay.
So, any more questions? So we're pretty much all good here. No more, huh? No more questions? Okay, thank you very much, Chris, for a great presentation. I really enjoyed, learned a lot. And to all the participants here, huh? Thank you very much for your time and support of CAMMSE. We really appreciate it. And this will mark the end of the Dr. Claudel's presentation. I hope you enjoy the rest of your day and also have a great weekend. Stay safe. Yeah. Thank you all.
Thank you.
Thank you.
Thank you.
Yeah. Bye-bye. Thanks.
Thank you. Thanks. Bye.
Bye-bye.
Bye.